We present co-abstraction, which is a method for identity-preserving geometric simplification of the models in a collection. We build on the hypothesis that a given model may have many valid abstractions, and therefore the most appropriate abstraction may only be found by considering all the other models in the collection. With our approach, we can obtain a consistent level of perceived abstraction within the collection without requiring the user to manually dictate the level of detail for each model. For a given model, our method first generates a spectrum of abstractions, each differing by the amount of detail they contain. The co-abstraction is later computed from the abstraction spectra by minimizing a joint entropy function associated with the collection. Our method is based on a volumetric decomposition of the model using the vertices of the original geometry. Using a probabilistic vertex claim and release algorithm, we perform volumetric primitive fitting and beautification. This enables the model to be represented with progressively finer details. Our approach extracts the major volumetric components using a set of basic primitives. The surfaces of each primitive are then beautified into polynomial surfaces that closely match the outer form of the original geometry. The resulting surfaces are then merged and blended when necessary, resulting in a watertight volume representing the abstraction. This process is applied in multiple steps, where each step identifies a new detail to be added or subtracted from the previous abstraction. Once an abstraction spectrum is computed for each of the models in the collection, we use an entropy minimizing optimization algorithm to choose the most suitable abstraction level of each model. This minimization tries to simplify the input models to the maximum extent possible while preserving the characteristic features unique to their shapes. We ran a user study to test two key aspects of our method: identity preservation and mutual consistency. For identity preservation, participants are asked to match a given abstraction to the correct original model. 6 different model collections are presented in 2 phases, once using co-abstracted models and once using fully abstracted models. This test measures how accurately and how fast the participants can do these matchings. The results of the first part show that co-abstracted models can be matched more accurately as well as faster compared to the fully abstracted models. This difference is even more significant for models that share similar base structures, as the full abstractions of such models become difficult to distinguish. In the second part, participants are presented a set of co-abstracted models. One model is left out for testing. From the abstraction spectrum of this left-out model, the participants are asked to choose the abstraction they believe best matches the detail level of the co-abstracted models. The results of the second part show that, statistically, humans have similar preferences when it comes to choosing the best abstraction level for mutual consistency. More importantly, this closely matches the abstraction level computed using our method. To conclude, we argue that an object may have many valid abstractions. However, the most meaningful abstraction can only be determined by considering the context in which the model occurs. With this work, we hope to have taken a step toward this idea.